So today we're going to start the new and the last topic of this whole class. That is Bayesian linear regression. And I imagine this will be useful to some of you for your project. But of course, you should not restrict yourself to only working with the models that we have covered. There's another dimension of doing a project at a 300 level course is to definitely explore things that interest you, and then maybe will involve reading accessible journal articles like the one that we did with the Gibbs sampler and stuff like that. So, but in any case, I think regression itself is a very powerful tool, no matter whether you're working in the Bayesian context or not. So it is important to introduce you all to the concept itself, and then in particular, how to implement Bayesian linear regression methods using, in particular, we're going to use JAGs in this case again. Okay. All right, so the regression type of analysis actually is going to be very well connected to the normal model that we have talked about at the very beginning. So you know that when you have an outcome variable that is numerical, using a normal model is a straightforward choice. And now, instead of just modeling the variable itself, we are trying to add a continuous predictor variables just to get us started. So that will introduce what we call the simple linear regression. Okay? And then we will once again use the CE sample to look at the outcome variable with one predictor that is a numerical predictor. So that will be the starting point. All right, so this is the equation one, that is the normal model that we used to know. Okay, so here we have IID stands for independently and identically distributed. Okay, so that is to say that all of the YIs, they follow exactly the same distribution, normal with mean mu and sigma as the standard deviation. So there is nothing specific to observation I as we set up the model in equation one. Okay. And suppose now we have another continuous variable xi generically, and we want to use this information in xi to learn about yi. Okay, so we still have outcome as yi, which is observation specific outcome. But instead of using equation one, which is a normal model IID, we're trying to introduce extra, which we're going to call predictor variable, to learn about yi in this case. So if we go back to the CE sample that we're kind of familiar with, let's just say yi is the log of the expenditure, which we worked before. And now we're introducing this xi to be the log of the total income. So pretty much, I still want to learn about the log expenditure of the consumer units in my sample. But instead of using a normal model, I'm trying to introduce and use the information that is contained in total income to model and predict the expenditure of the observation. Okay? So based on your knowledge, either with or without regression, is the model equation one flexible, you think, to include an xi? So we have this mu and sigma that is not specific to any observation, and that's the starting point. And given your experience, like I said, or even if you haven't seen a regression in the past, how would you think that we can use or include information from an xi that can be made into equation one to update the model to be a observation specific model? Okay, so that's the question. So for remote people, this is slide number 4, and I will use a breakout room for everybody remote, and then give you the time here and remote as well to discuss this before we move on. All right, any thoughts? If you have seen regression in the past before, how do people usually include any predictor variables into the regression model for a yi? Yes, Carl?
I think it's usually used to predict the mu in the normal distribution.
Yeah, right. So you will see that at least in the very or most basic form of linear regression is you're still going to have I think a shared sigma over here, but for mu, we will become to model it and in a specific way to write instead of mu, but then mu I. So you'll see that how to express the mu I in particular as we go along. In fact, the model specification for a linear regression model is not very different between the Bayesian context and the frequentist context. Okay, but of course we treat different things as random and different things as fixed between the frequentist method and the Bayesian method. So our focus is based on is mostly on how to figure out the Bayesian approach. Okay, so you will see that soon. We're trying to incorporate xi into a what we call mu I. So we're gonna have a group, not group specific. We're gonna have observation specific mu I, which, as you will see, will become a linear combination of an intercept and the slope multiplies with a predictor variables, which is hopefully what you have seen in the past before. So this is what we mean. We're going to adjust the model from the previous equation, that is a shared mu and shared sigma, to this equation 2, where the common mean is replaced by an observation specific mean, mu I. And then of course, the next step is how to link the mu I and the xi. So equation 2 is saying that each of the observation yi independently, so you see that instead of IID, we're using IND over here to represent its independent. So IID stands for identically and independently distributed. Right now, they do not identically follow the same normal, right? They follow its own observation specific normal, but we still assume that they're independent from each other. So this is why instead of IID, we have IND over here. And then the mean mu I is going to be observation specific. All right, so the next step is how to link the mu I and xi. And like I said, if you have seen regression in the past, this should be overall familiar to some degree as well. So the mu I, we're going to actually have a linear relationship so we're going to have mu I equals to a what we call intercept, and we use beta 0 because in Bayesian syntax or in Bayesian context, we think this is unknown. Okay, so we have beta 0 as the intercept plus beta 1, which is the slope, multiplies with the predictor variable xi. So let me pause here for a little bit. Beta 0 and beta 1, they are the unknown parameters in our model. That's why we use Greek letters for them. Okay. Xi, actually they're constants because they are given to us in the data set. So think about the log income of each record xi. Okay. And the mu I, as we know, is the average for each of the observations in the normal model. Okay. So in terms of interpretation, which shouldn't be very different from what you have seen before if you have taken anything related to regression, this linear function, which is the sum of the beta 0 and beta 1 times xi, is going to be the expected outcome with xi for the observation yi. Okay, so mu, usually, as you know, we use mu to represent a mean, okay, or expected value. And then we have now an index I, so we're looking at the expected outcome with xi for this observation yi. Beta 0 is typically called the intercept. So it's going to be the expected outcome when your xi equals to 0. Okay, so when xi equals to 0, the second term goes away. Okay, so your expected outcome ui just becomes beta 0, and that's why we call the beta 0 as the intercept to be the expected outcome when you have your predictor variable taking value 0. And then when you're working with thinking about what it means to have the beta 1, so typically beta 1 is called the slope. Okay, and what this is trying to express is that the increase in the mu I gonna have when we have the xi increase by 1 unit. Okay, so this is also thinking about, well, we're not thinking about beta 0 is fixed. We're looking at a beta 1 and the change of beta 1 that it's gonna have on the outcome, the expected outcome, which is gonna be mu I. So typically, when you're working with a numerical predictor like xi over here, we're thinking about 1 unit increase in your xi. It's going to result in beta 1 unit change in your mu I, which is the expected outcome. Like I said, I think if you've seen regression in the past before, the model setup, the interpretation of the intercept and the slope shouldn't be very foreign to some degree. And also, this could serve as a good review of how we think about linear regression in general. All right, so for Bayesian approach, clearly we need to identify which are the unknown parameters, and then we're going to give priors to them, right? And then use the Bayesian MCMC estimation to come up with the posteriors for them, and then we can summarize the posterior. So if I look at my entire model, right, of course, beta 0 is unknown, so it is one of the parameters. Right? Beta 1 is also another parameter. And another thing we shouldn't forget is, if you remember how the model was written up in the first place, so it's normal, mu I, and sigma. Okay, so sigma is another unknown that we'll have to estimate as well. Okay? So I have beta 0, beta 1, and also sigma. Some of you might be wondering, why don't I also treat mu I as random? Okay? So the thing is, if you look at equation 1, beta 0 is random, beta 1 is random, xi is fixed. So mu I, since it's a linear combination of beta 0 plus beta 1 times xi, so if beta 0 and beta 1 are already treated as random, I don't need to model mu I anymore because I have a deterministic relationship between them. So that is why we look at all of the parameters. We have beta 0, beta 1, and sigma. Okay? We are, of course, going to figure out how to give a appropriate prior distribution, a joint prior distribution for all of them. And then we're going to do our MCMC and MCMC estimation, including diagnostics, to make sure that the MCMC estimation has been done properly. And then lastly, summarize the posterior distribution of these parameters. Okay, so try to recall what we have done before, that every time we have a data model, in this case, is this yi independently follows its own normal distribution. And then we have a data model, we identify which are the parameters, and from there, we're going to give joint prior for all of the parameters. We're going to perform MCMC estimation, and in the end, come up with a joint posterior for all of the parameters. And then if the MCMC diagnostics are passed properly, then we should be able to summarize the posterior too for any of the inference questions you might be interested in. So for example, a lot of the focus for linear regression, simple linear regression, is by looking at beta 1. Because beta 1 is the slope, tells us how xi can affect, right, the outcome in the expected format. So depending on how you, what kind of posterior distribution you're going to get for your beta 1, as you know, for frequentist method, people like to do hypothesis testing, right, to figure out whether xi is a statistically significant predictor and all that. So in Bayesian context, as you recall from the very beginning, we also talked about hypothesis testing, okay? But instead of doing the null hypothesis versus the alternative hypothesis in the frequentist context, as long as we have its posterior distribution, we can pretty much quickly summarize, for example, a 95% credible interval, and we can directly calculate the probability that beta 1, for example, is greater than 0 or something in the posterior. So this is what we have seen before. But in this final unit, we're trying to synthesize everything together. Okay. So putting everything together, just want to show you different ways of expressing the model, because like I said, if you've seen regression in the past, there are many different ways that people will be expressing regression models. So equation 4 is one way you can write all of the parameters in. Okay, so earlier I was using normal mu I and sigma, but if you prefer this way, you can also just express mu I to be beta 0 plus beta 1 xi, and then you still keep your sigma. So in this case, equation 4 includes all of the parameters, right? Like, because earlier is only mu, and then you have a separate mu, like this is one over here. But equation 4 can be comprehensive in a sense that I know exactly what are the parameters I'm working with, and then this will be fine. Alternatively, some of you might have seen this kind of notation, that I'm writing out my outcome yi to be a mu I plus the error term. Okay, so epsilon is usually represented as the error term. And then mu I, as we know, is a linear combination of beta 0 and beta 1 times xi, so that's no different from before. But instead of writing out yi directly follows the normal, people like to write out about the error term, okay, follows a normal distribution, center at 0, and then with the same sigma that we were talking about before. So this kind of notation is really trying to break it down of how the yi comes out. So yi in equation 5 is saying that in addition to the mean that I'm trying to estimate, if I estimate beta 0, beta 1, I will have a good understanding about mu I itself. But as we know, the observation does not directly lie on that regression line that we're going to fit. Okay, the dot's going to be around the regression straight line that we're working with. So you're using this epsilon I notation to capture the error term. Okay, so regardless, both of them are talking about the same linear regression model. They're just different ways of expressing it. And you might have seen one or both in the past, but I just want to highlight they are really talking about the same thing. Okay. And like I said, if you have taken a course related to frequentist regression, this is what I circle or put in the box right now over here, because of the model is set up in this way that the error term is assumed to be a normally distributed distribution. Then that's why a lot of times in the frequentist method that you might have seen in the past, one aspect of doing the model diagnostics is to check if the residuals are normally distributed. Okay? And that is why I should say, because in the assumption of the model itself, that we already assume that the error is going to follow roughly a normal distribution, and that's why you check that condition after you have fit the model. Okay? But nevertheless, those are important in the Bayesian context as well. Okay. So another way I want to show you is to actually think about what regression line is really talking about. So the straight line that we're going over here, as we can see, is a particular straight line or the regression line that you might come up with. Okay. I remember earlier we wrote epsilon I normal, 0, and sigma. Okay. Yeah. So in fact, the straight line is being expressed, which is the regression line that we're fitting, beta 0 plus beta 1 times x, which is the straight line going over here. Okay. But the error term, eternally, you can imagine it as we are looking at a particular x, for example, the middle over here. Okay, for this particular x value, okay, I know that my observation is going to be roughly following a normal distribution around that point. So let me say that again. This is the x, for example, a particular xi that I'm working with. Okay, if I plug that in xi into this beta 0 plus beta 1 xi, I'm going to get the mean. Okay. So that's this mu I. Okay, mu I is this particular point at the middle. Okay. But we know that observations are not really, usually not really on the straight line itself. Okay, observations are around the straight line that we're trying to fit. So visually, what linear regression model is really doing is that the regression line expressing the mean, only the middle point. Okay? But we know that the observations for a particular xi gonna be roughly around this mean value, and the error term that we're gonna have follows a normal distribution. So that's why you see that this curve or 3 curves going on over here. Okay, we're showing them as 3 different normals. Okay? They're the same normal, by the way, because they're all of the same normal center as 0 and then standard deviation sigma. Okay? But linear regression, what it is really doing is that for the observations that we're working with, the linear regression line gives us a straight line that is going through the mean. Okay? And that's why we have this notation in the very beginning. Okay, so what we're estimating over here is about the mean, but then the observation is randomly around the mean with standard deviation sigma. So if you look at the graph one more time, let me just close this. Yeah, the straight line gives us the mean. It only goes through the mean. Okay? But the linear regression is not only just fitting about the mean. They're also trying to understand that sigma. Okay? And that sigma is the error term, or I should say the standard deviation of the error term from the normal distribution that we're trying to catch. Okay? And I should say, well, in this graph, because this is just trying to show you how it looks like when you fit the lines and all that. But of course, in practice, your data points are just something like this, right? And then when you do a regression line going through, okay, what we're trying to say of this model assumption and what this regression model is really doing is this straight line in blue is only capturing the mean for each observation. Okay, but then there's deviation, right, of your actual observation to the regression line, and that deviation is being captured by that sigma. And in our regression analysis, we're trying to estimate that sigma as well. Okay, overall makes sense? Okay, alrighty. So with that, let's just also take a look at, I think that's the CE data and the same sample that we had before, the CSV file posted on Moodle as well. Basically, I took log on both observations. Just to make the skewness a little bit better. And in this case, we are trying to use the outcome variable, which is the log expenditure in the y-axis, and the log income is the predictor in the x-axis. And this is pretty much the scatter plot that we're trying to understand. Okay. So of course, later on, you're going to see that, well, we're going to fit a regression line going through it. Okay. And the regression line is in particular beta 0 plus beta 1, sorry, times x. Okay. And then that will represent a straight line going through. Okay. An immediate observation, which we'll see soon, is that, well, according to Bayesian analysis, beta 0 is random, right? Beta 1 is random. So in the posterior, we can have all kinds of beta 0, beta 1s. So we're going to try to figure out how we can really say anything about a particular straight line going through. Compared to frequentist methods you might have seen before, it will just be a straight line, and you know certain standard error about beta 0 and beta 1 once you have done it. But from the Bayesian point of view, you will see that inherently will come up with the variability of beta 0 and beta 1 once you have fit them. So this will be our example going through. And the CE sample, like I said, now we include other variables as well. For the simple linear regression, we're just going to focus on the first two variables. So log expenditure will be the outcome variable, and then log income will be the single predictor for our illustration of a simple linear regression. But I include rural and race as well, because after we're done with simple linear regression, I want to give you an example of doing multiple linear regression, where you might have variables of different types. For example, rural is a binary predictor variables, okay? And then race is a unordered categorical variable. And we're gonna see how, not today, of course, today is mostly just simple linear regression. And then you will see later that how we can include binary predictors like race, like rural, sorry, and then unordered categorical predictors like race into a multiple linear regression. So this, I think, will expand your toolbox of analyzing data once we get to that point.